deal. Extra good behavior and no last names except for mine. Today is October 11th, 2011, and we are graphing.
Oh, wait.
Yes. Okay. Graphing the non-sinusoidal trig functions. The sinusoidal ones. I love that word. Hate this marker though. The sinusoidal. The sinusoidal functions are of course sine and cosine in all their variations, but you can also graph tangents, secants, cosecants, and cotangents. I am going to start with secant and cosecant because they're a little bit easier in my humble opinion. First off, what's the relationship between, let's say, sine and cosecant? How do they relate to one another? What's the word?
Reciprocal.
Reciprocal, yes, of my three favorite words. Joey got the correct one. So, similar to my idea of parent functions, where there's an original function you just have to know in order to be able to predict the variations. I am going to graph a sine wave. And it's going to be the parent sine wave, so it's only going to go from 1 to -1. It's going to start at the x-axis. What will the period be of just plain old sine wave? I hear several 2 pi's, and they are correct. So it has a 0 of pi, hits a value of 1 at pi over 2, hits a value of -1 at 3 pi over 2. I think I should find another color while you guys contemplate that. I may not have another color, which is too bad. Oh. We'll now pause for station identification. Okay. So in green, we have y equals sine x. In blue, I'm going to graph y equals cosecant x. Sine and cosecant are reciprocals of one another. That means at every point along its period, every point actually forever in both directions, the cosecant is the reciprocal of the sine. I'm going to start out with what I hope is the easiest question. What is the reciprocal of 1?
1 over 0.
1.
No,
Just 1.
1.
1 is just 1. Okay? So anywhere the sine is equal to 1, the cosecant is equal to 1. What's the reciprocal of -1?
1.
-1. The reciprocal does not change the sign, S-I-G-N, of the thing you're finding the reciprocal of. So the cosecant graph must be equal to 1 where the sine is equal to 1, and must be equal to the -1 where the sine is equal to -1. Those are the places where cosecant and sine intersect. From here, I need you to use a little bit of imagination. That's fairly straightforward. If you look at the sine wave, let's say from pi over 2 to pi, okay? Peaks at 1, and from there it is getting smaller. It is a decimal or fraction value between 0 and 1 everywhere from here down to the x-axis. In general, what do you get when you take the reciprocal of a fraction less than 1?
More than 1?
Something more than 1. Yeah, the reciprocal of 1/3 is
3.
3. Reciprocal of 1/4 is
4.
Reciprocal of 1 over 25 is 25. So the smaller this gets, what happens to the reciprocal?
It's bigger.
It's bigger. So as the sine wave gets close to 0, the cosecant function has to behave very differently.
Well, this is what we're learning.
Yep. And now what do you think happens when the sine wave reaches 0? What's the reciprocal of 0?
Zero.
There isn't one. We cannot define one. Hint, hint. We cannot define a reciprocal of 0, so undefined is the word we use. You guys are good today. So undefined is indicated with a vertical dotted line on a graph. This is a vertical asymptote. I realize we're doing this class out of order, so we haven't discussed vertical asymptotes in detail. I don't know if you guys got to them, but I'll give you the quick definition of an vertical asymptote in my class. The function approaches the asymptote, snuggles up to it, doesn't really touch it.
Yeah.
The never touches it idea gets a little bit complicated when we get to limits at the end of the year, but for now that'll work. Keeps getting closer and closer without touching it vertically. Okay? You probably did horizontal asymptotes with exponential growth and decay last year.
We did vertical.
Did you do to get to rational expressions? Okay.
I think so.
Okay. Now, let's go from pi over 2 back to 0. The sine wave from pi over 2 back to 0 goes back down, gets smaller and smaller and smaller. So its reciprocal will also get larger and larger and larger. And because the sine wave hits the x-axis at x equals 0, then the y-axis will also be an asymptote for the cosecant. 2 pi is another 0, so I'm going to draw another dotted line. And now, what happens when you take the reciprocal of a negative fraction?
It becomes
Yes,
negative.
one.
It's negative.
It goes down.
It goes down. It's the simplest way to say it. Yeah. You get a negative number with a larger absolute value is probably the correct math way to say it. Or just by example, the reciprocal of, say, negative 1/3 would be negative 3. So down here, the cosecant behaves like that. And you get these sort of staple shapes. If it helps you to remember that they look like parabolas, that may help you, but they're not parabolas. You could not take one of these and superimpose it over any parabola. Although people try with something called Taylor and Maclaurin series, and they get pretty close. But please remember they're not parabolas mathematically, but if it helps you to remember they look like them to graph them, go for it. They're more like staples than anything else. Or what do they call the things you in croquet that you knock the balls through? Wickets, is that what they're called? Is wickets what you hit? Oh, I don't know.
hit a ball.
Oh,
You hit a ball,
it's
but then
the
you-
gates.
Oh,
The
yeah.
gates.
Yeah, no, gates.
Yeah, okay, the
But
gates,
arches,
thank you.
the
Okay, they're arches. That's the word I'm trying to say here.
They're curvy.
There's a similar relationship between cosine and secant. If you hadn't guessed by now, my advice to you on graphing these is always graph the sine or cosine first, and then draw the reciprocals. Because this can get tricky as they shift. I'm going to jump from this fairly simple one to a harder example, because I think tangent may take some time.
Wait, but how are you getting where the vertical asymptotes are here?
The vertical asymptotes on the cosecant are the zeros of the sine,
Okay.
where the sine equals 0.
Okay.
Now the problem with that is when we start shifting up and down, it's no longer going to be where the sine hits the x-axis. It's going to be where the sine hits the where the sine wave hits the sinusoidal axis. That's a little bit tricky. I'm going to jump to an example of this. Can I go ahead and just tell you that the relationship between cosine and secant is the same, and jump to a secant example? Okay, I'm going to try and I'm going to jump right to a hard example, but I'm going to try and do it slowly. So, here we go. If you get that concept, here's something that'll help. So I'm going to say to graph y equals 3 secant. What do I want this to be? Yeah. Pi over 4 x plus 3. I'll leave k out for now. Okay, that's the graph. Here is my humble advice. Don't even think about this yet. Forget about it. And instead graph y equals 3 cosine pi over 4x plus 3 to start with. But don't forget to go back and fill in the secant afterwards. Okay, how would I graph this? What is my a equal to? 3. What is b? b is pi over 4. So what does that mean for my period?
It's
Good job. The period is 8. Joey has either gotten very quick at dividing fractions, or he has figured out the pattern that this is always going to be half your period. But the period, just remember what you would do is you would take 2 pi divided by pi over 4, and that would get you 8 in a few more steps. What is k equal to, my phase shift?
0.
0. And what is h equal to?
3.
3. I shouldn't have used 3 twice. Come on, you guys hopefully you're good enough to not get confused by that. Alright, so now I'm going to graph the cosine. Doesn't look like I'll need, if I'm just going to do one period in quadrant 1, doesn't look like I'll need to go negative at all. Okay, so my sinusoidal axis, 1, 2, 3, 4, 5, 6, at least 7. I'll show you why in a sec. The sinusoidal axis is y equals 3, correct? Is that correct?
Yeah.
Okay, I tend to make dumb mistakes, so double check me. It's a non-shifted cosine, so it's going to start at a peak. First, I'm going to draw my dotted line. This thing's going to go as high as 6. I know that from the amplitude. From the sinusoidal axis, it goes up to 6 and down to 0. The period is 8, so I'm going to put my 8 in, put my 4 in, put 2 in, triple this, put 6 there. And 0, 2, 4, 6, and 8 are the 5 numbers which show me the 4 spaces I have to deal with on this. It's going to start at a peak. It's going to 0, and by 0 in this case I mean hit its sinusoidal axis above 2. It's going to drop 3 units lower and hit the actual x-axis at 4. It's going to hit its sinusoidal axis again at 6. And it's going to peak again at 8, and this is 1 period of this cosine wave. And I truly hope all that was just review at this point. I will need some of quadrant 4. I apologize for that. Any questions on this one? On this cosine? One of my better upside down bells. That's kind of sad.
If ours looks more like a U, is that a, like, rather than yours is kind of out like a bell, and
Well-
mine is like kind of more like a U, is that okay?
Again, I'm going to grade you based on what you label, not your artwork, but you want to get in the habit of leveling this off because it's, remember, it's about to go back down,
Right.
and when you get to calculus, the fact that this has a horizontal instantaneous slope here gets very important. The fact that that's level. So you definitely, I need you to think of it this way. So try and draw it that way the best you can, but again, I'll grade you on what you label, not your artwork. So definitely label that this is a peak. Okay. Jen, I liked what you asked over there about the vertical asymptotes. Where would you place the vertical asymptotes of the secant graph based on this cosine?
At 4. 'Cause that's what this is.
Smart mistake. That is a mistake, but it's a smart mistake. Because remember, when we move, the zeros over there are where the sine wave hits the x-axis, right?
Right.
But what's our new x-axis?
Oh, so it's at 3.
Yeah, if you treat the y equals 3 as your new x-axis, Daryl and Michelle, where would I put the
2 and 6.
2 and 6? Because these are, if you think of h as your new x-axis, then what you already know can help you out over here. Otherwise, you have to sort of relearn it. Okay, line up as well as I'd like there. Okay, so those are my vertical asymptotes. Now, again, you have to think of this as your x-axis for behavior. But basically, a secant graph, just like over there, with a cosecant and a sine, a secant graph and a cosine graph will meet at their peaks and valleys. And where the cosine graph goes down, its reciprocal will go up. Where the cosine graph goes up in both directions, the secant graph will go down from that common point in both directions. And again, where there's a peak here, that is a valley on its reciprocal.
Will peak and valley at the same point be forever?
That is one of my better ones, actually. I'm kind of glad we're filming this one. If the A, B, K, and H are all the same, Noah, between a cosine and a secant, then the peaks and valleys are where they will meet. Does that make sense?
Okay.
That's only if the A, B, K, and H are all the same.
This actually makes more sense than my normal ones.
I'm glad you like it. If you're good at the sines and cosines, the secants and cosecants, just draw the sine and cosine first, and then figure out your new vertical asymptotes, and from the peaks go up, and from the valleys go down in both directions. And you've got your secants and your cosecants. Cosecants I never found much use for. Secants show up a lot in calculus. So secant graphs can be important in your future.
I don't get how you know that, like, how do you know for the top ones to put it in the far right and left boxes and not in the middle one?
Okay, I didn't really mean to make boxes, but I see what you're saying.
Yeah.
Okay. Follow me back over here a second, Tekin. If you look at the original function, the sine wave we did over here, all right? The cosecant, the blue, is the reciprocal of the sine in green. So over here, what you've got is smaller and smaller fractions, 1/2, 1/4, 1/8, which are going to lead to reciprocals of 2, 4, 8. As this gets smaller and smaller, this gets larger and larger. So what you're actually seeing is that mirror image behavior
and
here.
as that one gets larger, that one gets smaller.
Correct, because it's the reciprocals of negative fractions are going to be negative numbers with a larger absolute value, even more negative numbers. Now, that's kind of easy to see here because we can talk about between 0 and 1 and between 0 and -1. That's why you really have to think of that sinusoidal axis as being moving the x-axis and all its properties. Okay, so when you come back over here, if you pretend that your sinusoidal axis is your x-axis, then it's like this is going from 3 to 0 instead of from 6 to 3. Because as the cosine would be going from just 3 down to 0, its reciprocal would be going from 3 up to infinity. Okay, and the same thing with these values if this was 0. So your sinusoidal axis doesn't just move your function up, it really does recalibrate your whole graph.
Oh wait, why would it be 3 up to infinity? Why wouldn't it be another?
I was talking about the blue one goes from 3 all the way up to infinity in this
Yeah,
direction.
why wouldn't be another? Oh, because it can't go that way.
It can't cross the asymptote.
Yeah.
That's an excellent point. I should talk more about the properties of vertical asymptotes. They go up to infinity and you can't cross them. Okay? You can sometimes cross horizontal asymptotes. We'll talk about that later. But you can't ever cross a vertical asymptote in a function. So this does not keep going over here. That's another difference between these and parabolas. Thank you, Jen, for saying that. Okay, so any questions on this?
What happens if we put a shift?
If we put a shift in, everything moves, left or right. Again, just put the shift in the cosine and pay attention to where that will move your vertical asymptotes and you should be fine. I wish I had time for an example of a shift, but I gotta get the tangent and cotangent. They're a little trickier. Yes, sir? Yes, go up behind or up or something.
Behind me.
Yeah, go the long way. All right, yeah, this will be a little tricky on the shifts, and if I have time, I'll go back and do a shift, but I really want to start tangent now. All right, and again, for the shift, just put the shift in the cosine or the sine and draw your inside-out curves. All right, are you guys ready for
To rumble?
the part that, I don't know, let's see how you guys do. You guys are good with this stuff. Maybe it won't be as confusing for you guys. We'll ask brilliant questions that'll help. Okay. Tangent. Latin for touch. All right. To do graph tangent, I'm going to try and do something fairly difficult for me, which is be neat. Don't start drawing this graph yet, because it's going to be a little bit different. Do one y-axis to keep things lined up.
Wait, what?
That was just to help me line it up. Whoa, don't you do that? It's my clever trick. Wish me luck on this next part. The parent sine wave going from 0 to 2 pi, peaking at 1, valleying at -1. Attempting to match the scale, the parent cosine wave peaking at 1, Peaking at 1 on the y-axis, 0 on the x-axis. Need my pi over 2 for this.
So don't just do it yet. Still.
Probably not. Okay. Hopefully that's okay. That's about as good as it's going to get at this point, I'm afraid. Now, these dotted lines are not necessarily asymptotes. They're just to help me draw it in this case. Okay? So, you guys get that I'm trying to line up a sine over a cosine here, right? Okay. Can you see the, I apologize for all the dotted lines, but can you see the parent sine wave and the parent cosine wave in there? Okay. Here's why I'm doing it this way. If you guys remember, there's a relationship where the tangent of any angle equals the sine of that angle divided by the cosine of that angle, right?
Yep.
Okay. So, with that in mind, thank you. Come again. Shockingly, people are not immediately sucked into my math lectures.
Cosines, we're out of here.
All right. This relationship is not just true of the angles, it also is true of the functions as well. So what we can do is we can look at the specific points and get some points on the tangent, and that's a good way to start seeing how it behaves. So when, make this x instead, sine x, cosine x, tangent x. Let's put in some points. 0, pi over 2, pi.
So we should draw that first.
At this point, you guys are ready to draw it, yes. Okay. Now you should be able to draw that. Some of you probably neater than, Michelle definitely neater than I can. Wow, they get really more curved. There's like perspective in this. The way my y-axis is slumped. You guys can multitask a little bit. Can you tell me what the sine of 0 degrees is?
0.
Tell me what the cosine of 0 degrees is?
1.
1. Can you tell me what 0 divided by 1 is? 0. What's the sine of pi over 2, or 90 degrees?
Wait,
What?
wow.
1.
That's pi over 4. 1. These are just
Pi
these are
over 2 is
90. Yeah, these are going to be the 4 points of the compass on your unit circle. What's the cosine of 90 degrees?
0.
0. Almost said it. What is 1 divided by 0?
Undefined.
Undefined.
So how do we graph that?
Vertical asymptotes. Anywhere you get undefined, you get a vertical asymptote. What is the sine of pi? 180 degrees. Halfway around the unit circle.
Oh, because then it's a cosine, so that makes sense.
Okay. 0. What is the cosine of 180 degrees?
-1.
Negative 1. So 0 over negative 1 is 0. 3 pi over 2. What is the 270? What's the sine?
-1.
What's the cosine?
0. So it's undefined again.
Still undefined, yep. And back at 2 pi should be the same as 0, so that's 0 over 1 is 0. There's a lot we're skipping here. Joey tripped over one of them. But basically what we have is a situation where a tangent graph is going to be 0 at 0. At pi over 2, it's undefined. And you can check this with a few other points. Actually, I'll give you one thing. It's 0 to pi over 2. That's quadrant 1 on the unit circle, right? Is the tangent positive or negative in quadrant 1? Positive, Joey says with the yawn. Yes. For one thing, it's sine over cosine, and they're both positive in quadrant 1. So it approaches its asymptote something like this. And there's a vertical asymptote here at pi over 2. Okay? When we go over to pi, the tangent is 0 again. But I'm curious what the tangent's doing on either side of that 0. If you go back to the unit circle, between pi over 2 and pi, we would be in quadrant 2. Is the tangent positive or negative in quadrant 2?
It's negative.
Negative. It's got a negative slope over in quadrant 2, plus it's a positive sine divided by a negative cosine in quadrant 2. A little more time, I should have thrown some 45-degree ones in here. That would help us keep track of things. So it must come up from this asymptote in the negative direction, and from pi to 3 pi over 2, now we're in quadrant 3 where tangent's positive again, so it goes up something like that.
And then the next one.
It keeps repeating.
Yeah.
It will be negative again, just like the tangent is in quadrant 4, and it will come up from this negative asymptote and hit pi over 2 at 0, and if we're only lining up from 0 to 2 pi, then that's all we have to do.
Wait, can you explain those again? I understand how you're getting from 0 to pi over 2.
Uh-huh.
Because, or I get that it starts at 0.
Right.
And then because, how do you know it goes up and not down?
Great question. Okay. Tangent is slope, remember, on the unit circle? It's y over x, that's always slope. And picture from 0 to 2 pi as the slope of a clock hand. Where can I stand and do this? I can stand over here, sort of. Okay, so on the unit circle, at 0 degrees, Jen, we have a slope of 0, right?
Yeah.
From 0 to 90 degrees, what does the slope do?
It increases.
Until it reaches 90 degrees, and what do we call a vertical slope?
What is it? No slope?
Undefined.
Okay.
That's what we call them vertical. So that's what we've been finding. These are actually the points of a vertical slope. So comparing the slope, this is going to be awkward, but imagine if the y values on this graph are the slopes of this line. As I move this, okay, Jen? See what's happening? As I move the tangent around the unit circle, this line gets bigger, and as the tangent gets to an undefined slope, this function gets to an undefined value. So you can follow the slopes. Now, as I get past 90 degrees, I have an extremely negative slope, don't I?
Yeah.
Then the tangent graph must have an extremely negative value.
Right.
And as I go from 90 down to 180 around the unit circle, this graph must go from an extremely negative value up to 0, just like the slope of my marker does as it represents the radius on the unit circle, with the tangent being the slope. As I go down here, I have positive slopes again. I'm going past 180 degrees on the unit circle and past 180 degrees on this graph, and I get an increasingly positive slope until it's undefined again. So if you really get that the tangent is the slope of the radius of the unit circle, then this graph can't behave any other way.
And then because in the 2 pi, I get that it's at 0. Oh, because it went up, so now it's going to go down again.
Yep, here's a negative undefined slope. Here's a negative slope, negative slope, negative slope, negative slope, negative slope, 0 slope. And that's how the tangent behaves as it goes around the unit circle.
And then if you were to do like another like period of it, then that one
Would
go
keep
up,
going up.
And then
Yep. Interesting point about the period. I want to make that in a sec. The other thing we could do, Jen, to take a look at these, and I had this graph here and could have done that, but between 0 and pi, positive sine, positive cosine. What's a positive divided by a positive?
Oh.
Between pi over 2 and pi, positive sine, negative cosine. Positive divided by negative.
wait, we did something like that last year.
Yeah, when you learned, probably when you first learned this relationship on the unit circle.
It was way before the unit circle.
I have no idea what that was.
We were able to just get numbers, and then it was like a number thing. This is
And
like
then-
what I've been saying in the beginning, but
That
it's
you did
not.
some of this
It's
last year?
not. And then
Okay.
based on that, you like have to. And if it's a positive, you know it's just up, and if it's negative, you don't do it with real number. Like
Rational, you did sign analysis with rational
Yeah,
expressions.
yeah.
That's what this is like. Okay, yeah, we're gonna get back to that in the spring. Okay? So you can also just, like over here, between pi and 3 pi over 2, you have a negative divided by a negative, so the tangent must be positive. Okay? Interesting point about the period. This pattern winds up repeating twice as often as sines and cosines. So what do you think the period is of a tangent function?
just pi.
Just pi. It's got half the period of that. I'm going to draw a neater parent tangent function over here, and tell you the points I expect you to be aware of, and start talking a little bit about how the shifts get more exciting.
Wait, so the one you just drew wasn't considered a parent function?
It was a parent function, it's just very small, and I can't fill in some details that I'd like to. So that is, I'm going to graph the exact same thing, but I'm going to do it a little bit differently. Okay, as Michelle pointed out, it does keep behaving the same way over and over again. So the point I'm interested in now is just from negative pi over 2 to pi over 2. This is the most commonly talked about period or repetition of a tangent function. Negative pi over 2 and pi over 2 will both be vertical asymptotes because they are places where the cosine equals 0. If the cosine is in the denominator, zeros in the denominator are what create your vertical asymptotes, which do go on forever. So from here, I'm going to fill in a little more carefully now. Try to draw this a little more carefully. Here is my interesting point. I call this a point of interest on a parent function. It's a point I think you should be aware of, and your graph should represent that you're aware of it too, either by labeling or astounding artwork, whichever you are better at, or both. Why am I filling in the point pi over 4 comma 1? How do I know that's on a tangent graph?
Because you said that like the period tangent is half the period of a sine and cosine, and so in order to like make sure that it correlates like properly, half of pi over 2 is pi over 4, and then that's when it's going to be like at 1, so like it carries on. It makes sense.
Very smart. No, that's very smart. That's very smart. It's even well said. I was just thinking, what's the tangent of 45 degrees? 1. So if you plug pi over 4, 45 degrees into tangent, y is the tangent of that, so that's 1. But I like your way of thinking about it too. I like how you took it straight from my explanation over there. That was very smart. This is a shortcut. So, and similarly, I know that at negative 45 degrees, the tangent is negative 1. So I know it passes through those points. And that does make this a little trickier to draw. In fact, I'm sure I just messed up what's called the point of inflection, but you don't need to worry about that. Okay? So I'd like you to be aware of these points. Now this is where I have to go back to my original definitions of A, B, K, and H for a moment. And because amplitude isn't quite going to cut it with this. Amplitude works great for sine, great for cosine, does a great job of helping you find where to start on the secants and cosecants. Amplitude doesn't really help as much here, and amplitude wasn't the generic definition of A. You guys remember on my original description of any function's behavior, what I said about A and B originally? K and H don't change, but for any function. You remember that or know how to access it in the notes quickly, or do I even have time to wait for that? Probably not. So here's what I'm going to say. Okay, A now is what you multiply all the y values by, ending with a preposition. It's bad grammar. I'm in a hurry. A is what you multiply all the y values by. If you think about it, that's the same thing as amplitude on a sine and cosine wave. Peaks at 1, multiply 1 by the amplitude, that's how high your sine and cosine waves go. B was originally what you divide all the x's by, but in this case there's a similar shortcut. In sines and cosines, B was 2 pi over the period, correct? Since a tangent only has a period of pi, as Michelle just told us, what do you think B is now? Not quite. 1 what? Well, it was 2 pi over the period for sine and cosine because 2 pi is the period of a sine or cosine wave. A tangent repeats itself every pi degrees.
So then B is always 2.
Nope, it's not the pi that goes away. B is going to be pi divided by the period instead of 2 pi divided by the period. And the period of a tangent is going to be pi divided by b, your coefficient. Okay?
This is only for a tan, right?
Only for tangent and cotangent, which I may or may not have time for. You may be struggling a bit with cotangent tonight, but it's a similar pattern. This is also true for cotangent. Okay? K and H behave exactly the same. K and H move everything counterintuitively left to right or intuitively up and down. They don't change. Again, B has to be factored out first for K to behave the way I've taught you. Okay, so you may have to factor a common factor out of the two terms inside your tangent function first, just like we did for sine and cosine. K and H I'm not going to redefine, so let me do a quick example of this. Actually, you know what I'm going to do first? I'm going to give you the parent cotangent function first. And what you can do for cotangent, if you want to understand a little bit, is you can duplicate what I did over there, but put the cosine on top. Remember, tangent and cotangent are reciprocals. So cotangent is going to be cosine over sine. What that leads to, well, here's a quicker way to do it. Cotangent is also the reciprocal of tangent, right? What's the reciprocal of 0, basically? It's undefined. There is no reciprocal of 0, it's undefined. What is the reciprocal of 1? 1, so at pi over 4, the cotangent will also be 1. What is the reciprocal, do you think, of an undefined line?
0, but that sounds kind of silly.
It sounds kind of silly, but it'll work that way. Right? At 3 pi over 2, I'll ask you to just take my word for it that the cotangent is -1, and if you don't believe me, draw a unit circle. And at 3 pi over 4, and pi. At pi, the tangent would be 0, so the cotangent will be undefined, and a cotangent function winds up behaving like a reflected tangent
Mr. Balbo, what's
Yes.
the second number on the number line?
pi, the one I just drew the line through?
Yeah.
Pi over 2. Thank you for asking. So if you take the tangent, and I apologize my scale's so off, it doesn't look like this, and you reflect it about the y-axis and then move it over pi units, you get a cotangent. And we'll talk tomorrow about how you can actually express tangent and cotangent in terms of one another just like you can with sine or cosine.
If you don't draw an arrow through your vertical asymptotes, is that okay? At the
I
end?
mean, at the tops and bottoms?
Yeah.
That's fine, I'm not going to get picky about that. You know they go on forever, right?
Yeah.
And we're good.
And what's that X at the top? Is that just an arrow?
Up here?
Yeah.
That's supposed to be an arrow. I rushed that too much, sorry. So this is your parent cotangent function. And I'll expect you to know that on the parent, the y-axis is a vertical asymptote. It zeros at pi over 2. Pi is your other vertical asymptote on this first period of it. And it passes through pi over 4, 1 and 3 pi over 4, -1. All right, that's the cotangent parent.
So does it line up eventually with at 2? Like the positive?
2 where? 2 on the y, 2 on the x? What are we talking about?
2 on the y.
Up here?
Yeah.
It'll hit 2 wherever the value of cotangent equals 2. I have no idea what that angle is.
Oh.
Wait, so that if we were to like keep the period going, then it would just
Start up
sit
here
there?
and go like
Okay.
that. Yeah. And if we kept going in this way, we'd start down here and go up like that. So that's cotangents. Let me do an example of a shifted, moved around tangent real quick. And get you the homework, which is not yet online, but I'm hoping will be by the end of the day. Okay, so if I just were to give you y equals 2 tangent, pi over 3x minus pi over 3, I won't do a vertical shift yet. Okay, what's the first step that some of you still struggle with on this one? I think that's not phrased that way. What's my A equal to? 2. What is B?
B is.
We're at the period yet, just what's B?
Oh,
B is pi over 3. Then what's my period going to be?
pi.
Very good if this were sine or cosine.
Ah.
But this is just pi divided by pi over 3. Which will get you 3. Okay? So I got half the period, so that changes. What is my K?
0.
Positive.
Negative, or no, it's
Pi
just
over
3 over
Positive
pi.
pi over
Pi over 3. 3 over pi.
Oh wait, why am I flipping it?
Oh no, wait. I know it.
Oh, we have to
Right. It's 1. No.
1. Daryl and Joey said it together. It's 1. You have to factor out the pi over 3 before you can figure out the correct shift.
K. Right. K.
It's 1.
I was thinking of H.
Yep, and H is
Is
0. There isn't one. There's no up or down on this one. Okay, so how does this play out? Well, there's no amplitude, so we have to, again, think of A as a multiplier. That's the main difference. Other than that, this is like, just like one of the more annoying sine or cosine ones we've already done. Now, the period is 3. And so I'm going to start numbering this. 1, 2, 3, 4. The period is 3, but it starts over at 1 instead of over at 0. Now, so you can think of it like x equals 1 is like our new y-axis. On the parent function, what is the tangent doing at the origin? Crosses. What's its y value there? 0. Then that's what this is going to do at 1. Okay? A tangent, that's a little tricky. Okay, a tangent normally goes from negative pi over 2 to pi over 2 is the period I like. Okay? What would that be with a period of 3? Instead of pi over 2 to pi over 2, what would that be? The parent function has half of its period to the left of the y-axis and the other half of its period to the right of the y-axis.
Oh, would that be?
So then we'd go to
Oh,
the
that would be,
go to that normal y.
What would that be?
Wait.
Can I draw?
Wait, what would the
So
y
what-
be?
what
Oh,
are
would
we
that be
doing?
one?
Trying to figure out how this period of 3 changes things.
Oh, so would the last
Oh.
one be? Oh, so, would that be
Oh,
1.5?
Daryl's got it. Okay. The tangent parent function has half of its period on one side of the y-axis and the other half on the other. So if the period's 3 and there were no phase shift, we would expect this to go 1.5 to the left and 1.5 to the right. I have to rush this a little bit, I apologize. Because there's a phase shift, we don't go out to 1.5, we would move that over to 0.5.
why?
Because there's a phase shift of 1. And then we don't go
I get
to
it.
then we don't go to 1.5 here, we go out to 2.5.
But we're not.
So these are my new vertical asymptotes.
So a 2.5 and negative 1.5.
And negative 0.5. I'm sorry, negative 0.5. Thank you, Jen. I was drawing the wrong space. I apologize that the decimals will be a little hideous, but I'm going to have to do this a little bit quickly. Now, the tangent zeros halfway in between its vertical asymptotes. Halfway in between negative 0.5 and 2.5 is 1.5 plus this. So that should be right at 1, correct?
Yes.
Okay? Halfway in between 1 and 2.5. Okay,
Wait, shouldn't
now, here's the way to picture this
The
one.
period is 3.
Period is 3. Negative 0.5 to 2.5 is 3. Apologize, I got to rush, guys. I really want to finish this one. Halfway in between 0 and pi over 2, you've got pi over 4, 1. Halfway in between 1 and 2.5, is 1.75. But instead of passing through 1, we have an a of 2, which means I have to multiply that by all of my y values. So instead of passing through 1 on the y-axis, it passes through 2.
Wait, how are you getting 1.75?
Pi over 4 is halfway between 0 and pi over 2, right?
Yeah.
Then this point that I'm interested in is going to be halfway between 1 and 2.5. Okay? There'll be a corresponding point over here, which will be 0.75 over from there, 0.25. And we'll talk more about that
Oh wait.
tomorrow. That point will be there at 0.25, -2. And this looks something like that. Wow, that's a bad drawing of it.
Close enough.
Close enough. It's a little harder than, again, since I labeled it, we'll count that. A little bit harder than the, this is probably a little bit harder than the homework questions will be tonight. So let me find that really quickly. Okay, Tekin, you can go ahead and kill that.